Hey guys, welcome back to our channel Get Play Soon. In this video, we're going to solve a LeetCode problem number 162. That is, find peak element. This is also the second problem that we are going to solve in the binary search playlist. Peak element is nothing but an element which is greater than its neighbors. In the given example, index 2 value is 8. It is greater than its neighbors index 1 and index 3. So 8 is greater than 3 and 4. So 8 is considered as peak element. Now, an array might consist of many peak elements. We are supposed to return an index of any one of the peak elements in this problem. Possibilities of peak elements. Here, if the array is arranged in the decreasing order, the peak might be in the starting of the array. And if the array is arranged in the ascending order, then the peak will be at the ending of the array. And in one array, we can find many peak elements. We are just supposed to return any one of the peak elements. To do this, we have linear search, which means iterating throughout the array and finding an element such that the element is greater than both its neighbors. So iterating takes O of n and complexity. But in the LeetCode question, they have clearly mentioned the problem is supposed to be solved in O of log n time. We will use binary search. A binary search is a search where we reduce the search space in half at every iteration. Now, how to modify our binary search to find the peak element? For example, consider this array. In this array, while finding mid in the binary search, if you landed at index 1, and you can notice that index 1 is greater than index 0 and less than index 2, which means this path is like increasing path. Similarly, in this example, consider index 3, where index 4 is less than index 3 and index 3 is less than index 2. So looking at the both index 1 and index 3 here, you can see that in index 1, the peak is to the right side. And in the index 3, the peak is to the left side. Which means in the index 1, it is going in the ascending order to the right side. In the index 3, it is going in the ascending order to the left side, which means it is in the decreasing order from left to right. Now, based on these graphs, we can write an approach to solve this problem. As you already know, in the binary search, we calculate the mid element. If the mid element is less than mid plus 1 element, then the peak cannot be on the left side of the mid because the array is in the increasing order in that particular region. So, we update left to mid plus 1 to focus on the right half of the array. Similarly, when we compare mid plus 1 and we know that mid is not less than mid plus 1, which means mid is greater than or equal to mid plus 1, it means the peak element might be at or left of the mid. Then we update right to mid to include mid in the search space and also focus on the left of the array. Here you can notice in the first two statements that we are only considering and comparing only one element, one neighbor, that is mid plus 1. Basically, one element comparison is enough because based on that element, we are shifting to left half or right half. We continue this process of updating left and right until left and right cross. When the condition is met, which means we have found a peak element, and then we return the index of the peak element. For example, we have this array here. First, as the binary search, we are supposed to calculate the mid. So we have 6 elements. So the first element being 0 as in indexing, as in arrays, indexing starts from 0. The last element is 5. 0 plus 5 by 2 gives you 2. Index 2 is the mid element. When we compare mid and mid plus 1, we see that mid is greater than mid plus 1. So we update right is equals to mid, focusing on the left part of the array, including mid. Okay. Now you can see the left and right pointers are updated. So again we do the binary search iteration where we find the middle element, that is index 1. So mid is equals to 1, the element 3. Now again we compare mid and mid plus 1 elements. When we compare mid and mid plus 1 element, that is 3 and 8, we see that 8 is greater than 3. So we update left is equals to mid plus 1. Right pointer is at index. And left pointer will also reaches index 2. There we can say that we can stop the iteration. Now index 2 is the peak element and we can return 2 as a peak element. Now let's see how to do this in programming. First we have this main function where we are creating integer numbers array with the following numbers. Now we are creating a variable peak index where store the result of peak value. passing this nums array into the find peak element function, and once we get the result from the function, we will print out the result. Now look at the find peak element function. We have this parameter called arrays nums. Now here we are creating integer n is equals to nums dot length. First we'll know the length of the array. Then we will initialize our left and right pointers as 0 and n minus 1. Now we will start the loop from left to right, just as in binary search. Similar to binary search, we will calculate the mid element. Here, why are we not using left plus right by 2, and why we are using left plus right minus left by 2? This we have already discussed in the previous video. This we use to overcome the overflow errors. If you haven't watched it, please go and watch my first video on binary search. Now once we calculate the mid, we will compare our mid element with the mid plus 1th element, and if mid element is less than mid plus 1th element, then we will update the left pointer, or else we update the right pointer, and we continue the while loop until left and right meets or left crosses right. This is how the left pointer will go to the peak element, and once it is done, we will return the left index. The left index is nothing but the peak element index. Let's discuss about the time and space complexities. The time complexity is overflogging because we are using binary search approach, and we are reducing the search space in every iteration to half. That's why the time complexity is overflogging. Speaking about space complexities, we are using constant space and we are not creating any extra stuff, so the space complexity remains over 1.